Okay, this is part two, continuing on, and I realize that probably some of this stuff is not going to be useful to the vast majority of us, but it is interesting, I think, to understand what epidemiologists do and to have some context for different research that you might look at or critique or appreciate in the future. Here, the textbook continues on with single and multiple causes, and they're highlighting now rules for determining whether a specific organism is a cause for a disease. So, Pasteur work on microorganisms led to this formulation. Others, I believe, continued to refine it. These are the rules for determining whether a specific organism is a cause for a particular disease. The organism must be present in every case. The organism must be able to be isolated and grown in pure culture. The organism must, when inoculated into a susceptible animal, cause the specific disease, and the organism must then be recovered from the animal and identified. Anthrax was the first disease that was demonstrated to meet these rules, and there have been other diseases identified as well as understanding of the chemical poisoning process and how it is a cause. However, for many diseases, both communicable and non-communicable, the aforementioned rules by Koch are inadequate. Koch's one of the individuals who continued and built upon Pasteur's original work. Many causes act together, and a single factor, such as smoking, may be the cause of multiple diseases. In addition, the causative organism may disappear when a disease has developed, making it impossible to demonstrate the organism in the sick person. So the four rules that were presented here, they're of most value when the specific cause is a highly pathogenic infectious agent, if it's chemical poisoning, or some other factor and there are no healthy carriers of the pathogen, which can be an uncommon occurrence. Four types of factors play a part in the causation of disease. All are necessary, but they are rarely sufficient to cause a particular disease or state. These include predisposing factors such as age, sex, and previous illness, enabling or disabling factors, precipitating factors, and reinforcing factors. The term risk factor is commonly used to describe factors that are positively associated with the risk of development of a disease, but that are not sufficient to cause the disease. The concept has proved useful in several practical prevention programs. Some risk factors, like smoking, are associated with several diseases, and some diseases are associated with several risk factors. Epidemiologic studies can measure the relative contribution of each factor to disease occurrence and the corresponding potential reduction in disease from the elimination of each risk factor. However, multi-causality means that the sum of the attributable fractions for each risk factor may be greater than 100%. The effect of two or more causes acting together is often greater than would be expected on the basis of summing the individual effects. This phenomenon, called interaction, is illustrated by the particularly high risk of lung cancer in people who both smoke and who are exposed to asbestos dust. The risk of lung cancer in this group is much higher than would be indicated by a simple addition of the risks from smoking and exposure to asbestos dust. Multiple causes and risk factors can often be displayed in the form of a hierarchy of causes, where some are the proximal or most immediate causes, precipitating factors, and others are distal or indirect causes, enabling factors. Inhaled tobacco smoke is a proximal cause of lung cancer, while low socioeconomic status is a distal cause that is associated with smoking habits and indirectly with lung cancer. In epidemiologic studies linking one or more causes to a health outcome, it is important to consider to what extent different causes are at the same or different levels in the hierarchy. If a cause of a cause is included in the analysis together with the cause itself, the statistical method of analysis has to take this into account. The identification of a hierarchy of causes and the quantitative relationships between them will provide one way of describing the mechanism of causation. So, for example, low socioeconomic status is associated in many industrialized nations with more tobacco smoking, which is associated with higher blood pressure, which in turn increases the risk of stroke. Causal inference is the term for the process of determining whether observed associations are likely to be causal. The use of guidelines and the making of judgments are involved. The process of judging causation can be difficult and contentious. It has been argued that causal inference should be restricted to the measurement of an effect, rather than as a criterion-guided process for deciding whether an effect is present or not. Before an association is assessed for the possibility that it is causal, other explanations such as chance, bias, and confounding have to be excluded. A systematic approach to determining the nature of an association was used by the U.S. Surgeon General to establish that cigarette smoking caused lung cancer. And obviously, you couldn't do a prospective cohort study because it would take how many years? 20, 30, 40 years for lung cancer to develop. So you'd have to use things like a case control study design and to set up your statistical modeling to account for all the other potential factors that can contribute to lung cancer. Now, there are a set of considerations for causation listed in the sequence of testing that an epidemiologist should follow to reach a conclusion about a cause of disease. So those are listed here. I'm not going to read through these, but you should pause the recording and read through them. Again, these are considerations for helping to determine causation. When you're done pausing the recording and reading through them, go ahead and continue on. All right, we're going to continue on. Now, what are the best studies to prove causation? Strong one is a randomized controlled trial. We looked at examples there earlier in the term. Randomized controlled trial, that jumping injury prevention study showing that there was a decrease in knee injury incidence between females who trained and females who didn't train. Cohort studies are a strong way of proving causation. Same with case control studies. What do we know about other ones, like a prevalence study? That they are weak, that they're a starting point. Okay, that's all for this week when it comes to lectures.